Today I'd like to start a new topic called recurrences. And a recurrence is simply a description of a sequence of numbers. For example, I could say the first term in the sequence of numbers is 1, and I could say the nth term in the sequence of numbers is equal to the n minus first term plus 1. So what sequence of numbers does this describe? Well, the first number in the sequence is obviously 1. We've specified t1 is 1. And then tn equals tn minus 1 plus 1. So to get t2, for example, we need to take t1 and add 1 to it. So the second one would be 2. t3 is equal to t2 plus 1, according to this rule. So we take 2 and add 1 to it. t4 is equal to t3 plus 1. So the next number in the sequence would be 4, and so on and so forth. You can see this is a pretty common sequence that we've described by using this recurrence relation. You've seen recurrence relations before. For example, the Fibonacci numbers, right? We have the sometimes referred to the 0th Fibonacci number is 0, and the first Fibonacci number is 1. And then we have that the recurrence f of n equals f of n minus 1 plus f of n minus 2. So to get f of 2, we take f of 1 plus f of 0. 0 plus 1 is 1. Then for f of 3, we would take f of 2 plus f of 1, so we'll get 2. F of 4, by using this rule, will be 3. And you can see that we're starting to build up the Fibonacci numbers 0, 1, 1, 2, 3, 5, 8, 13, and so on and so forth. It turns out that understanding recurrences, and in particular finding simple formulas to calculate the nth term in a sequence described by a recurrence, are very important tools in computer science, and they're particularly helpful for analyzing recursive algorithms that we'll see later on in the semester. The classic recurrences problem is the Tower of Hanoi problem. So this is sort of a famous old problem where there are 3 pegs and there are a bunch of wooden discs that are placed on the first peg. And there's a very large one at the bottom and one that's slightly smaller on top, and then another one, another one, so on and so forth. And there are, let's say, k of these wooden discs, and they slide up, so you can slide them. You can slide this top one off, and you could place it on one of the other pegs. And there are basically 2 rules. You can only remove one disc at a time from the top. So, for example, I can't remove this disc right here. I can only start by removing this one, and no I should say smaller discs or larger discs cannot rest above smaller discs. So for example, if you were to take this disc right here, this top uppermost one, and slide it off and move it to this peg, that would be fine. Then so this one would be gone. So this one's gone. And then we'd have this second block here, you can't put it on top of this one because it's larger. You could move it over here, but you can't put a larger disk on top of a smaller disk. So you can only remove one disk at a time, and you can't put larger disks on top of smaller disks. And the goal is to move all the disks in the same order onto peg 2. Okay, so we start in this configuration where all the disks are on peg 1, and what you'd like to do is end in this configuration where all of the disks are in the same order but on peg 2. Okay, so the problem is, how do we get from, or how many steps does it take to get from this particular configuration to this particular configuration? And I obviously can't just pick up all of them off of this peg and transfer them all onto this peg, because I can only do one at a time, and I can't put larger disks on top of smaller disks. Okay, so how do we do this? Well, we can sort of use induction to come up with a strategy. So, for example, let's say that we have 3 pegs, and let's say that k equals 1. So we just had one disk. How would we solve the problem? Well, there's only one disk, so we could slide it off here and move it to the second peg. So for k equals 1, solution is simple. So now let's write a predicate that says P of k says that the towers puzzle for k disks can be solved. Okay, and what we'd like to do is we'd like to prove P of 1, P of 2, P of 3, and so on and so forth. So this is a proof by induction. Let's show that if we can solve the puzzle for P of k, this implies that P of k plus 1 is true. So for all k, P of k, let's prove that for all k, P of k implies P of k plus 1. Well, can we prove it? So we've proved that P of 1 is true. That was the base case. Okay, now how do we do P of k plus 1 given that P of k is true? Well, let's assume that we're given initially k plus 1 disks on this peg. So here's the k plus first disk. And then there are k disks on top of it. Okay, so think of this k plus first disk as sort of, these other two pegs are sort of attached to the ground. Think of this k plus first disk as the ground. Okay, so by induction, we know that there is a way to solve the Towers of Hanoi puzzle for k disks. Okay, so we know that there's a way to transfer these top k disks onto this second peg, and we'll just leave this k plus first disk totally unmoved. We'll just never use it. So there is a way of transferring by induction these top k disks onto this second peg. Therefore, there's also a way to transfer these top k disks onto the third peg. After all, the second peg and the third peg are identical. So by the inductive hypothesis, we can move into this configuration. Here's that k plus first peg, that k plus first disk. Here are the 3 pegs. And we have these k disks that were on top of this k plus first disk, we now have them on peg 3. Okay, then what can we do? Well, we can then move this bottom k plus first disk. So we'll have the following configuration. In one move, we can move this k plus first disk from here to the second peg. So we'll move it from here to the second peg. And then, on the third, these two are the same. So I guess this is configuration 1, which we achieved by the inductive hypothesis. Then this is configuration 2. We move this disk to the second peg. And now, by induction, by the inductive hypothesis, we know that, again, we can move all of these k disks onto some other peg, either this peg or this peg. So let's move them back to peg number 2. So this is configuration 3. Well, I guess there should be another peg here. And this is, again, we did this by the inductive hypothesis. Okay, so by using the inductive hypothesis and treating this k plus first disk as sort of part of the ground, we're able to maneuver from this initial configuration to this configuration. Then we switched the bottom disk here, and we moved all the disks over there. Okay, so we showed how to solve the puzzle for k plus 1 disks. Okay, so that's interesting, but what we're really interested in is how many steps did we take? Or how many steps does it take to solve the puzzle? Okay, so let's write a recurrence to try and figure this out. So we know that, so let's let t of n be the number of steps required to solve the Towers of Hanoi. On n disks. So we know that t of 1 equals 1. That was sort of our base case in our inductive argument. We just needed to move one disk from peg 1 to peg 2. Now, what about for t of n plus 1? Okay, well, remember the first thing we had to do was we had to use the inductive hypothesis and move all of these disks above this bottom disk onto peg 3. So we had to use t of n steps, to move one disk. So if we had n plus 1 disks, we had to use t of n steps to move those n disks onto peg 3. Then we had to use one move to move the bottom disk onto peg 2. And then we had to use t of n more to put those disks that were on peg 3 back onto peg 2. So I guess to draw this, we have our initial configuration. Then we had to move all of these n disks over here. So we had this configuration. So this took t of n steps. Then we had to move this bottom one over here. So that took 1 step. And then we had to move all of these back onto here. Sorry, my drawing is so bad. This took another t of n steps. So to do n plus 1 moves, we had to do t of n plus 1 plus t of n. So we got t of n plus 1 equals 2 times t of n plus 1. So we have t of 1 equals 1, and we have t of n plus 1 equals 2 times t of n plus 1. So now we can start to write out a few terms in this particular sequence.